Hi, this is part 3 of lecture 5 for heat transfer MEC 3820 for the summer session 2 of 2020. So where we're going to start off is with both the Cartesian and the cylindrical form of the heat equation. So on the left-hand side, you see that there are terms that are dealing with each of the particular coordinates in Cartesian x, y, and z, and in cylindrical there's r, the radial, phi, the azimuthal, and z, the longitudinal. Now they're all second-order terms, and they each contain the thermal conductivity of the material. But in the cylindrical, there's an extra term here. It's 1 over r squared, and the z term doesn't have that. We're leaving open the possibility for thermal energy generation, and they both have the unsteady term where we allow the temperature field to vary as a function of time. Now, what we'll start with the 1D steady state no heat generation form. So the Cartesian we've already looked at, but for the cylindrical, what we're going to end up with is just the radial term, and you'll notice that there's a 1 over r over here. But since the right-hand side is going to equal 0, we can simplify that just to the second order term. So now this is the type of geometry you're dealing with in the cylinder. Typically we're going to have an inner radius, which we can call R1, an outer radius, which we'll call R2, and either the inner side is hot and the outer side is cold, showing the heat rate moving outwards, or of course the converse can be true, where we would have a hot outer side and a cold inner side, and the heat rate, the thermal energy, would be moving from the outer portion of the cylinder inward. So the cylindrical solution starts again with this second order ODE, and if we go ahead and separate our variables and integrate twice, we're going to end up, as we did when we looked at the specific solution for the Cartesian case, we're going to end up with two unknown constants which we can satisfy or make a particular solution by imposing some boundary conditions. So in this case, we will just use a constant temperature boundary condition. So at radius 1, we'll call that the inner radius, we'll have temperature 1. At the outer radius, we'll have temperature 2. So when you go in and substitute those boundary conditions into the general solution, work through your algebra, and you'll end up with this particular solution. Now it's important to note that there's logs in these solutions. Now this term is just the log of R2 over R1 really is tied up with your thermal resistance, and this is a constant, but the log of the radial coordinate divided by the inner radius will give you a logarithmic profile. So what you see here as we move from a high temperature at the inner core, 150 at a radius of 0.25, to a colder environment, colder surface at the outer surface at a radius of 0.55, we get this characteristic drop off of temperature, but it's not linear as you would expect in the Cartesian form of a plane wall. We have this logarithmic curve. So now we can take a look at going back to the Cartesian form of a 1D steady state with heat generation. So in this case, this is the ODE, and we can simplify the ODE a little bit by breaking up the second order term. But we'll note that the Egen term, the energy generation term, which again is watts per cubic meter, is a constant, and we'll assume K is a constant as well. So this is just a quick cartoon of what we're looking at. But as we're going to see, we're going to want to make the width 2L, and we're going to find in this solution that it's going to be helpful to have the origin of our coordinate system at the midplane of the wall. So this is the ODE. Go ahead and integrate twice, and we would have the general solution, which is quadratic, again with two unknown constants, which we can solve using boundary conditions. And you'll notice in this case, I'm going to use negative L as the left-hand wall and positive L as the right-hand wall, and again using constant temperature boundary conditions. When we do this, you end up with this type of particular solution. Again, it's a quadratic. One thing to note is that if you let T2 equal to T1, this linear term was going to drop out, and you'll actually get a symmetric solution, which is what I'm plotting here. You'll notice that for this one, T1 and T2 are the same values. I'm just using a generic term for K and a generic term for the heat thermal energy term, which is Q dot. Again, this would be capital Q dot, or no, sorry, this would be E gen dot in your textbook. I just forgot to change the notation here. A couple things to note is that at the center line here, the derivative is 0, so all the energy that's generated here, assuming this is steady state, all the energy generated on the left-hand side of the wall is going to pass out the left-hand wall, and all the energy generated on the right-hand side of the wall, or the midplane of the wall, will again pass out of the right-hand wall. So we can use this we can use this concept to describe what an insulated wall is. So here's just a better picture. I'm a little squatter, but at least I have my 2L in here and I'm marking where the midline is. And again, this is the type of plot that we had. Well, now this is where the dt dx equals 0, and if dt dx equals 0, that means the heat rate, which is Q dot equals minus K a dt dx. If dt dx is 0, well, the heat rate's 0, so that means there's no heat passing across this boundary. And what that essentially is that if there's no heat crossing across this boundary, it would act like an insulated wall. So the solution for a wall with energy generation where one half is insulated is really just half of this solution that we've just looked at. And a couple things to point out is that at the high temperature, the highest temperature in a wall with energy generation with one side insulated is against the insulated wall, as you would think, and all the rest of the energy is going to move out of the left-hand wall. So the next thing we'll take a look at, we just finished taking a look at the composite wall, and we're used to this thermal circuit, and in this case we'll have what we're looking at is a high temperature at TS1, a lower temperature at TS2, thus we have a heat rate or a constant heat rate of watts, in this case just watts because area is being, I'm using the capital Q dot term, so this would be just watts, but as we're looking at it, this would be little q dot because I'm not specifying the area, so this would be a flux. So I really should come back and change this to q dot where the q is a little q. So, and we would have this interface temperature TAB, which is something we can solve for. So in this case, we have TS1 is the temperature node. The thermal resistance for the wall A is LA over KA. Then we get to temperature TAB, and then we get to the thermal resistance of wall B, which is LB over KB, and finally getting to the temperature of the second wall. And if we want to know what the total heat rate is, and again, this should be little q dot, and this should be little q dot. So I'll change those when I post these up. But this is the total temperature difference between the left-hand wall and the right-hand wall, and the total thermal resistance of the wall. Again, the thermal resistances are in series, so they add up. So the last thing we'll take a look at is the concept of what would happen if you have a composite wall with an embedded heater. So an embedded heater is a source term that is different from energy generation because it's assumed to have no volume, i.e. zero thickness. We looked at this briefly yesterday in class when we solved the example problem of the car defogger. We said we had a very, very thin film that's placed on the inside of the window, and there was a certain amount of energy generation put into it, or a certain amount of heat flux coming out of it. So that's the case here. We could put a thin, basically a thin foil heater, is sometimes the way it's called in different textbooks, in the middle of, and sandwiched in the middle of two plates of different material. So it looks very much like the composite wall, except there's a source of heat coming in here. And if the source of heat makes the temperature of the heater greater than either TS1 or TS2, you'd have this situation where energy is flowing both out the left-hand wall and out the right-hand wall. Not necessarily, though, because we could have a situation where, say, this was a furnace of some sort, and it's very, very high temperature, and it's actually warmer than the heater temperature. Well, then you would have a flux of energy moving from this environment out here into wall A, and then you'd have an additional energy from the heater And both of those would be coming out of the right-hand wall. But the way I'm drawing a circuit here is the assumption that the temperature of the heater is greater than either of the wall temperatures. And what you have here is sort of a broken up thermal circuit with a source term. And that source term is Q heater. Again, the way I've drawn this, these should all be little q's, or you can assume I know a certain amount of area. So this, if I know the area, this is watts. If I don't know the area, this should be little q dot 2, and it would be watts per square meter. So just keep that in mind. So in this case, we would have three equations. We could say that Q1, using Fourier's law, is the temperature of the heater minus TS1 divided by the thermal resistance of wall A. Then Q2 would be, and again, remember these should be little q's, little q dots because they're fluxes because there's no area here, would be temperature of the heater minus TS2, the temperature difference between the heater and the right wall, divided by the thermal resistance. And the third equation for closure here would be that Q1 plus Q2, right, if it's in steady state, the heat that's leaving the walls must be equal to the input energy or the input power of the heater itself. All right, so that gives you sort of a comprehensive look at the different types of problems that we can look at in one-dimensional conduction. We'll probably pick up in the next video just a little bit on how to solve a problem with a composite cylinder, but pretty much that is going to do the bulk of our one-dimensional heat conduction. All right, so that concludes lecture 5, and look forward to seeing you for lecture 6.